Well, as you saw in the previous clip, thoroughly addressing the critical task of prevention can save lives, and especially when unexpected conditions occur. Following the several disasters that occurred during that period of 2001 through 2010, NIOSH researchers were involved in pretty extensive research to improve best practices in the prevention of fires and explosions in other areas too, but also in the critical area of mine ventilation. Two NIOSH researchers, Eric Weiss and Alex Smith, have been involved in this type of research, and they're going to give us some good insights in the next discussion, which is going to be on best practices aided by recent research and possibly technology transfer. I'm going to give a brief bio on each of them first. Alex Smith is the Deputy Chief of the Fires and Explosions Branch of the Office of Mine Safety and Health Research in NIOSH in Pittsburgh, Pennsylvania. He has a Master's of Science degree in Chemistry from Duquesne University and has been with NIOSH for 32 years. His main area of research is the prevention of spontaneous combustion in underground coal mines. He's also conducted research in mine fire prevention, detection, and extinguishment. Eric Weiss is a senior research mining engineer and team leader for the explosions team as part of the Fires and Explosions branch of NIOSH Office of Mine Safety and Health Research, also in Pittsburgh. He has an MS degree in mining engineering from the University of Pittsburgh, and for the past 30 years has overseen the research conducted within the experimental mine and surface facilities at the Lake Lynn Laboratory. His main area of research is in the detection and prevention of underground dust explosions and the strength evaluation of mine ventilation structures. So, with that said, I'm just going to basically throw out a general question for each of you, since you've got extensive experience in research. And what are some of the topics of the research over the past 10 years that has aided in improving prevention of fires and explosions, and possibly mine ventilation, if you wish, and the state of technology, if you will? So, Alex?
The last 10 years, recent years, a lot of our research has been focused on responding to the belt panel report on use of belt air at the face that came out of the Miner Act in 2006. And a couple of the things that we've been working on are the recommendation number one, and the fact that they're using belt air at the face, and does this ventilation have any effect on the effectiveness of the suppression systems, because the original regulations were written for no ventilation. So we did a lot of work at airflows up to 1,400 feet per minute to make sure that the systems still functioned as they were meant to be. And also the fact that the size of long walls and the size of panels are getting so much larger that they've gone to much wider belts than were originally used when the regulations were written. So we've done a lot of testing on 8-foot wide belts because there's so much larger amount of combustible material there. And the size of the drive areas is so much bigger now that, you know, the installation of the sprinklers is a little different. So the effective ventilation has been one of our primary areas of interest. Along that line, we were, I think out of the 20 recommendations, about 11 of them were directly addressing fires and belts and things like evaluating improved technology. So we've been doing some research to look at different types of suppression agents, additives to water, additives to the different types of chemical systems and things like that. And one of the things that we found was that with the higher ventilation flow, one of the powder systems, actually the hoses were burned up because of the ventilation flow, making the system ineffective. So the vendor or manufacturer went back and redesigned that so that won't happen. We've been working on an area using the old MFire program, which is a mine fire ventilation code that was developed about 30 years ago, and we modernized it so that it's user-friendly now. It used to be that you had to know Fortran and you had to put things in a very specific format. Now we've modernized it so it's Windows-based, and we just put it out on the web in January or February so that everybody can use it and has a simplified graphical user interface. And a third thing I want to mention is the work with atmospheric monitoring systems. That was another recommendation of the Minor Act of the Belt Panel report. And so we've been evaluating in our safety research coal mine at Brewston, since Lake Lynn's not available, using an AMS and looking at different sensors at different locations for different purposes. AMS we've found is not a one-size-fits-all. Just because you have an AMS and a CO sensor at each location isn't necessarily the best way to use these systems. And so we're looking at other sensors, where the best places to use them, to put those sensors are, and subjecting them to tests with different materials and different ventilation flows and things like that. One of our goals in the next couple of years is to tie that, feed the results of that, or the data from the AMS into the same system that MFIRE's in, because MFIRE is supposed to be a training tool where you can simulate fires, but in the case of a real emergency, we're hoping that you would be able to take real-time data into the system and actually be able to tell what the situation is in the ventilation streams away from the fire, and where the best escape ways are and things like that. So that's our goal of tying it all together. I think that's sort of a synopsis of the program at this time.
From the explosions point of view, from the explosions that's occurring since 2001, we're unfortunately seeing an upward trend of more explosions as time goes on, which isn't something we want to see. So especially since SAGA, we've been kind of doing some emphasis on seal research. You know, with the 20 PSI seals, that was based on explosions coming from the active side. And, you know, now the explosions, especially at SAGA, resulted from within the sealed area. So there's a lot of research going on there. There was an influential NIOSH report that came out, I think it was in 2007, from Dr. Ziff. And, you know, that provided recommendations on what seal strength should be, and that was later adopted by MSHA in the regulations. For explosion control, you know, we're looking at the prevention and mitigation of explosions. At first, we were looking at the coal dust. You know, the regulations of the 65% in intake airway was based on a coal dust survey back in the 1920s, which was a much coarser dust because of the mining mechanisms, you know, back in those days. But now with the longwall and the much more mechanized mining, they're producing finer coal dust. Finer coal dust requires more rock dust to make it inert. So we've been, you know, we have a recent study here, a research project that's emphasizing looking at rock dust itself, rock dusting practices. We're looking at sampling methods for, you know, what is a representative mine sample. And even though we still do fundamental research both in the lab, you know, and, well, till Lake Lynn closed in the experimental mines, but really, we really like to take the research and make it to, you know, to practices, R2P as we call it. And because if we could do all the research and put all the reports out that we want, but unless it's implemented within the mining industry to make it safer for the health and safety of miners, we're kind of spinning our wheels. So with that said, more recently we did a comprehensive mine dust survey. We were in cooperation with MSHA there. We looked at, you know, mine samples from around all the districts around the country, and we found that the coal dust, instead of being a mine-sized dust like in the 20s, which is only 20% going through like a 74 micron, like a flow coal dust size, it's more like 40%, at least as an average in one of the worst districts. So from there, we did full-scale explosion test at Lake Lynn, and we found that we need, you know, roughly 70, you know, upper 70s of rock dust to make it inert. We also did thermodynamic calculations, you know, modeling, and also looked at foreign practices. And from there, that's where the 80% came from. We put out an influential report, and then unfortunately, it was adopted later by, by MSHA for 80% incombustible for the mines. But what a lot of people don't realize, especially probably the rank and file members that are working in the mine, is it only takes 5 ounces of coal dust over a 1 foot area of mine entry, which is really less than a half a coffee cup of coal dust, to propagate an explosion. So how do you prevent that? You have to properly rock dust it. Because if you do have that small methane ignition, and it doesn't take anywhere near 3,000 cubic feet as the video showed, just a few hundred cubic feet is enough to scar up that coal dust because of the expanding wave of the gas burning, to scar up the coal dust and have the flame introduced into that coal and that be ignite. If you don't have the right amount of rock dust, excuse me. And really, for every ounce of coal dust that you're generating at the face, you need 4 ounces of rock dust to make it inert. And so we've been, doing a lot of research, looking, what is the best rock dusting practices. Ideally, you want to marry that rock dust with the coal dust, because this way, as it's going down the entries and spreading through the returns, it's coupled with the rock dust. Now, how do you know you have a representative sample? I heard some people saying, white is good, and white is good if you're looking at rock dusting, but how do you know you have enough rock dust there? And, really what happens is you take your samples, you take that representative mine sample, and then you send it off to a laboratory for analysis. Well, that could take days or weeks to accomplish. And, but fortunately, and after a lot of years of research, we did commercialize the coal dust explosibility meter, that when you take that representative dust mixture, now you can instantaneously, it's down in the mine, get a reading for what the rock dust percent is. It actually tells you whether it's explosible or non-explosible. You need that rock dust or don't you need? And you can immediately go in and add the rock dust if you're in an area that's deficient in rock dust. So that's been commercialized since last August, and I believe there's about 200 units out there, and I would encourage all mine operators to use that, because instead of, you could instantly make the change you need. There's probably a lot of other things, but.
Yeah, I'm sure there are, but I can see that, I think all of us can see that there's been a pretty direct impact on what's happened since 2006 and 2007, if you will, on where we've been headed with some of this new technology, and even offering some newer insights on what a better fire suppression system and things like this might be. So thank you very much for sharing all of that. I'm interested very much in the M-Fire, the modernized M-Fire, and does that do the simulation as well as show the spread of combustion products?
Well, because we're the government and we didn't try to put in a good graphical interface, a user interface, because there are commercial companies that do that. And so what we did was made sure that we wrote it so that it was compatible with existing commercial packages, and then their programmers can go into the common memory and pull things out and graphically display it. So ours is just a word display, but it's much better than it was.
Excellent, ready to be adapted.